Good morning. I am Sharan Santhanami. Today I am here to present our work on building extremely fast and efficient NFVs with Unikraft. Before we start on this topic, let me introduce myself. I work as a software specialist at NEC Laboratories Europe, and I am part of a team of 8 researchers who are working as a part of the systems group in our lab. One of the projects within our group is Unikraft, and this work contributes towards the port of DPDK on top of Unikraft as such. So for today's talk, we have structured it in such a way that we begin to discuss what is existing out there. Then we move on to introduce Unikraft, the motivation behind Unikraft, and how everything is structured within Unikraft. Then we talk about how to integrate DPDK libraries on top of Unikraft. Then we speak about the functionalities which Unikraft should provide to support these DPDK libraries. And we make a performance evaluation between a LinuxVM as well as a Unikraft image. And we discuss about the synergies of the two projects, Unikraft and DPDK, and how it fits into this ecosystem. So when we began, what we had in our mind is something like the diagram in the slide, where we have a guest operating system, and we have KVM as a hypervisor, and the host and the guest interact with one another through a para-virtualized framework like Vertio. And then this framework was further optimized with something called vHostNet to further improve the performance of this communication channel. And DPDK came along with its own vHost user, which further enhances this communication in our bottleneck system. But one part of this picture which has been left untouched is the guest operating system as such. We believe we can do better with the guest operating system. We believe we can specialize the guest operating system, wherein we take in only the required components needed by the application into the guest operating system. Thereby, we optimize it for something like a boot time or image size or even memory requirements for an application as such. And if we are only running specific application within the guest operating system, we could also reconsider the necessity for having kernel and user space separation within the guest operating system as such. Thus, if you're focused on a particular use case in mind, then Unikernel seems to be a good fit for that specific image as such. So if we were to make a comparison between a virtual machine image and that of a Unikernel image, it looks like something like this. And in a virtual machine image, you have a number of applications, and we have a large number of library pool, and we have a single monolithic kernel. From an application needs only some subset of these libraries from the library pool and some specific kernel components. Contrast this with that of a Unikernel image. A Unikernel image is built with one purpose in mind. Thereby, you only need an image which has the specific libraries and the specific kernel components with the application as such. Just to summarize a Unikernel image, what a Unikernel image is a purpose-built image with a thin layer of the kernel embedded into the application as such. Thereby, the application as such has to select which are all the libraries it needs and which are all the kernel components it needs. Since the kernel is embedded into the application image as such, the necessity for kernel and user space separation is no longer needed, and whatever was a syscall in a virtual machine image now becomes a function call within the Unikernel image as such. And since we are picking and choosing components needed by the application, we can specialize the entire software stack right from the kernel to the libraries to the application as such. Where do we realize the potential of a Unikernel? We can realize it in terms of faster boot times because it needs only a few milliseconds to boot a Unikernel, whereas it takes few seconds for a virtual machine image. It has lower memory footprints. For example, a Unikernel needs only a few megabytes in size, whereas a typical virtual machine needs few hundred megabytes or a few gigabytes in size of memory. And also, it has a higher deployment density, so it's easier to pack a lot of Unikernels. And its performance is comparable to that of a regular virtual machine image. And also, since we are only baking what is necessary for an application into the final image, it has a reduced attack surface because it contains what an application needs. And also since it has only those necessary components, it is as a smaller trusted computing base as such. So a Unikernel looks quite promising, right? It has good performance, it has quite a nice isolation features, instantiation time and image size. But why? The question is, why hasn't it been adopted more often? There are a number of reasons for it. Building a Unikernel is quite tedious. It sinks a lot of development cycles to get it right. And since you're doing it for each of the specific application, you keep repeating the same process again and again, and it becomes a bit tedious as such. And the other part is specialization is quite hard to build as such, because when you're specializing, you need a way to establish dependencies between the different components in the library pool and the different components in the kernel. And the kernel and these components need to have a well-defined interface as such. So bringing up this interface definition is also quite a difficult task as such. Also, since you want to run off-the-shelf application on top of these libraries, you need to make sure that you stick to a standard interface so these off-the-shelf applications can run on your library pool and on your kernel components as such. So with this, we decided to come up with a tool where it makes it easier to build Unikernels as such. So with that in mind, we had these common objectives in mind. We wanted to make sure most of these components were reusable, so we don't have to throw away any effort taken to build a specific application as such. So we wanted to build as much minimal basic blocks needed to build. We came up with a lot of basic blocks so that we can support a wide range of use cases as such. And also we needed to make sure that we have necessary tools to make sure we can establish these links between the different libraries and the components. And also we needed to make sure that the generic components or generic components are separated from specific platform specific or architecture specific components, so that you can use those generic components across the different platforms. And we wanted to support a wide number of hypervisors as well as architectures. So with this in mind, we came up with a tool called Unikraft, where everything is a micro library or library in itself. And the two prominent components in the entire ecosystem are the library pools and the build tools. With the library pool, what you can do is you can enable or disable a specific library pool, and the build system provides you the necessary convenience to do that. And also you can establish a dependency between one library to another, or one library and a kernel component. And this library pool also includes the OS components which are decomposed as such. So how does it affect? So, and also Unikraft is open source, which is BSD licensed. So how does it take to, what does it take to build an application with Unikraft, right? Let's take an example and let's run through it. So if we take an application like an typical DPDK application in L2 forward, we needed to select which are all the libraries which it needs to select those libraries. These libraries also includes something specific like kernel components also. For example, NetDev provides you a net device interface. So you need that in order to support an L2 forward application as such. And then Unikraft provides a different set of platform architectures which it runs on. So those specific libraries which are specific to a specific platforms need to be selected as such. And also the architecture specific code. And once these are selected, the Unikraft build system as such bakes your final image together, and you have your final executable image to run on a specific platform. So when we started our work on DPDK, this was the mental image we had to port a DPDK image to Unikraft as such, where we have an DPDK application, and we have something like a libuk DPDK, which provides the Unikraft functionality to a DPDK application, and it interacts with the internal Unikraft libraries as such. But we also had some design considerations into account when we had this mental image also. One of the advantages of the DPDK library is its modularity, and also the benefit of Unikraft is its modularity. So we wanted to retain as much modularity as possible. So to do that, we needed to make sure that the build system of Unikraft can understand the build system of DPDK. Thereby, it can use its modular libraries as such. And we wanted to find out where are all the possible cases where we can optimize the guest operating system, whereby you can simplify a lot of operations for a DPDK application message. And also the final constraint, which is for porting any library, is we wanted to minimize the changes within the upstream code within DPDK as such. So to make sure these build system compatibilities are matched, we first compare and contrast the two build systems as such. Unikraft build system is kconfig based, whereas DPDK build system has some auto config generation happening. And also Unikraft build system has some specific variable naming convention, whereas DPDK also has a similar naming convention, which needs to be translated from one to another. And also it had something called export sims in Unikraft, which tries to hide unnecessary functionalities from a library to other libraries as such. Similarly, DPDK had a version map equivalent. So in order to address these differences, we came up with a solution using a typical Unikraft approach, which is to build a library around it. So we came up with this library called DPDK build library. What it does is it processes the makefiles of DPDK and translates it to the makefiles understandable to Unikraft as such. The advantage of doing it is we can add a DPDK library as such to Unikraft, and Unikraft can then translate all its necessary dependencies to a Unikraft build system understandable makefile as such. Thereby, what advantage we gained is we were forward compatible, right? So as long as there was no build system change in DPDK as such, we can adapt all its libraries necessary to Unikraft without any further changes anywhere else. And also this library contained, if you have any specific configurations within DPDK, this library contained those configurations also. So with that in mind, we came up with this sort of an architecture diagram or a building block diagram where we retain as much as the DPDK libraries are concerned. For example, this RTE, ETHDev or the memory pool, M pools or M buffs were not changed one bit within Unikraft. Whereas for the abstraction layer, we needed to add some specific Unikraft specific code, which we'll talk about later. And apart from that, there are two libraries which are of consequence here, which are the UK ring and the UK PMD libraries. We will talk about these libraries further down the top. Yes. So then the next part of our discussion was how to specialize the guest operating system message. We looked at three parts where we could optimize the Unikraft guest operating system message. One is the memory management system. The second is the device management system, and third is the scheduling part. In terms of memory management system, what Unikraft provide was a static memory image where we have huge pages of 2 gigabytes mapped into the first 1 gigabyte of the address space. So thereby we only support 1 gigabyte of memory, and thereby we have a one-to-one translation between a PA and VA within a physical address to a virtual address within that of a Unikernel. And from an application perspective, an application can specify or reserve a memory range from the Unikraft Unikernel. Thereby you can make sure that this is specific to, you can reserve this memory region, and you can take this memory region and use it for your memory buffers already. And also it is possible to implement multiple allocators to understand which allocator is best suited for your specific application message. In terms of the device management itself, what Unikraft provides you is Unikraft just probes the devices and lets the application take over the device controller altogether. So Unikraft identifies which are all the devices necessary for an application and just hands it over to the application. And the application, it's up to the application how to handle these devices as such. You don't need any additional file system or anything else to handle these devices as such. And finally, for scheduling as such, Unikraft gives you the ability to make sure that you can run an application. An application can hog the CPU cycle until it can yield to another thread. So Unikraft uses a cooperative scheduler, thereby it runs an application can run a task without minimal interference from the Unikernel as such. And also, if it is possible, if necessary, we can also completely do away with the scheduler and run the entire application within a polling mode where everything is event driven, or an interrupt driven thing. So next, what is needed from Unikraft to support a DPDK libraries as such? So we compare and contrast how typical data flow works between a Unikraft library and a DPDK library. So on the left, you have the DPDK workflow, and on the right, you have the Unikraft workflow, where you have an application wanting to send, calls the RTETH burst in DPDK and UK NetDev burst, and then it calls the Vertio drivers to send out the data out. So you need, and also here, DPDK libraries handle mbuffs, whereas Unikraft libraries handle netbuffs as such. So there is a difference in data structure between the two libraries. So we needed a way to mangle from one data structure to another also. A similar diagram for the RX part of it. I'll skip this part. So what is the difference between a netbuff and the mbuff as such? So with a netbuff, what you have is you had a packet data with a netbuff. You had this netbuff structure, and then you have the user private data within which is the application's usage of the netbuff, and then you have the packet headers and the packet data. Whereas if you take the equivalent of an mbuff, you had this mbuff buffer, then you had the packet data, and you had some private data for it. So we needed a way to mangle from one netbuff to an mbuff as such. So we came up with this UK ring library, which does this mangling from one data structure to another. And also the poll mode driver translates the call, anything which is happening within the DPDK context, to that of the Unikraft context within the NetDev. So thereby, we were able to translate from a netbuff to a mbuff and mbuff to a netbuff with just these manipulations, whereby we point the private data of a mbuff to the netbuff and the private data of a netbuff to an mbuff. Thereby, it's easier to translate from one another. And finally, we talk about the performance evaluations. Here, we used two systems. One was the packet generator bar receiver, and the other system is the one which runs LinuxVM or a Unikraft VM message. The one it is a Sandy Bridge server with 6 cores on it. And we were using DPDK 1908 QEMU version 4, and the Linux kernel, the host kernel and the guest kernel were 4.19 dpi. And in terms of the next graph, where it shows the baseline performance, what we do here is we vary the packet sizes from 64 bytes until 1500 bytes, and we measure how much throughput we get in terms of billions of packets per second. So what we gain is in terms of we measured it in 4 mechanisms. One is using the vhost user, and which is the DPDK accelerated version, and the vhostnet, which is the kernel accelerated version. And in terms of Unikraft versus DPDK comparison, we are quite similar in transmission performance as such. Similar performance we did for the RX throughput, where the RX part of Unikraft with the vhost user is slightly slower than, is about 11.5 million packets, whereas the RX of LinuxVM was around 13 million packets for the minimal packet size, and for the rest of them was quite matching. So there are some bottlenecks within the RX which we need to figure out, which is part of the future work as such. So in the previous 2 experiments, what we did was a packet generator keeps sending packets, and we drop the packet once we receive it or once we send it. Here we did another experiment, which is like a key value store. What we did was a packet generator sends you a stream of packets. We receive the packet, we read some specific, based on the values in the packet, we read a key value store, and we send out the packet out. So with that, a single core is now processing the receive of packet, processing some data within the packet and sending it out. And we made a comparison of that with the LinuxVM and that of a Unikraft, and with DPDK and Unikraft with NetDev running. And all of them were quite similar in terms of 6 million packets per second. And in terms of resource usage itself, what we observed was, in terms of memory usage, Unikraft needed to run the DPDK application. Unikraft needed just 1 gigabyte of memory, whereas LinuxVM needed a 6 gigabyte of memory. So it's about 6 orders savings. The boot times of Unikraft is about 87 milliseconds, whereas the boot time of a LinuxVM is unoptimized, is about 12 seconds as such. And the image size comparison is, the Unikraft image is about 1.4 megabytes in size, whereas a LinuxVM is about 2.5 gigabytes in size. So it's about a huge order of magnitude difference between, in terms of resource usage as such. Finally, the next part of our of this journey is, we needed to add support for SMP drivers, SMP support, so that we have multiple CPUs. And also we wanted to try out running DPDK drivers instead of Unikraft drivers, which were run, so that we can keep it up to date. So if you find this work interesting, you could also, for further references, I have put down some of the links, you can refer it. And thus, to conclude my talk of Unikraft, we made a comparison. Unikraft provides you multiple platform support, a specialized guest OS, whereby we optimize for image size, memory consumption, and also the boot times at the same performance. And we have a simpler device management for a DPDK application. And we provide increased control for an application compared to that of a Linux guest VM. And in terms of DPDK provides you the benefit of a highly optimized network stack, a specialized VNF functionality, and a lot of untapped potential from the DPDK drivers as such. So I think the 2 projects go hand in hand in the VNF domain, and it is a benefit that we use Unikraft as a DPDK image in the virtualized network functions as such. If there are further questions, I would like to leave the floor for further questions. If you have any questions, please ask. Thank you.